here again. We have some exciting talks all day today. So I'm just actually going to turn it over to Luisa Rebull, who's going to talk about authentic research in the classroom for teachers and students. Let's give her a warm welcome.
Thank you. Thank you very much, and thanks to the organizers for inviting me. So I just wanted, especially since everyone's still waking up, I thought we better define some terms here. So the text you can't read there is from the description of this conference, and they talk about remotely located, relatively small optical robotic telescopes, where a lot of the telescopes I use are indeed robotic, and they are distantly located. They just happen to be in orbit. So I'm going to expand the definition of robotic telescopes a little bit. And they're not necessarily optical for me. And certainly we talked about lots of radio telescopes yesterday. And one of the things I wanted to emphasize is that the professional archives and the high quality data products make sharing and using this data worldwide really easy, not just for professionals, but for the education community as well. Also, in the description of the conference, to talk about high school and undergraduate students, I'm going to also include working with high school teachers, because I personally think it's really hard to beat the leverage of working with teachers, because each one of the high school teachers I work with will talk to and educate more high school students than I will in several years. In just 1 year for the teacher, they reach more people than I do in a year. So I find it hard to beat that kind of leverage. So I'm going to include working with teachers. So the astronomy data in the classroom ecosystem is broad indeed. I find that they can kind of be broken down into more or less 4 categories, and they all have very different audiences and challenges and goals. So citizen science, it's basically doing something small to contribute to the whole. Everyone's playing a small role. You don't need to know a lot of programming or even a lot of astronomy and astrophysics in order to contribute, but they're still excited to be contributing. You can have projects that use real data, but that are reproductions of very simple or done projects. So for example, rediscover Hubble's law. You can work with projects where the participants are contributing real data. And they might be using a combination of new and archival data or just the new data. And an example of that might be watch this star for a week, add your data to the past 6 months monitoring, and find the exoplanet that we know is there. And then the last broad category is original research, where you're doing professional quality data and doing real science. I want to emphasize that, like a real biological ecosystem, all parts of this ecosystem are important. Each of these categories is valid and worthy. There's no value judgment in this ordering. Each of these kinds of projects reaches very different kinds of people, very different numbers of people in terms of students and the public. But I can sort of think of that as sort of a funnel, right? Where the broadest part of the funnel is the simplest citizen science, where you can contribute and it reaches many, many people, but you don't need to know a lot of programming or engineering or astrophysics. So as the funnel starts to narrow, you have the working with real data, which is reaching fewer people. So you can sort of think of the widest part of the funnel. The most interested people from that widest part of the funnel might go down the funnel and start to work with real data. That's going to reach fewer people than citizen science does, and you do start to need a deeper understanding of programming and of data and astrophysics. Then contributing real data reaches even fewer people, and in order to do that, you need to understand what you're doing, at least with your own data, and how it fits in. And the lowest, even further down the funnel, is original research, which is very few people, and you really, in order to participate, you need a really deep understanding of what you're doing and why. And the very tip of the funnel, I would think of as grad school. But again, there's no value judgment. All of that is important because they're reaching different numbers of people and different groups of people. So I can think of that funnel as a continuum, and you might justifiably argue with me that it's not one-dimensional. But in the context of this talk, we're going to think about it as a funnel. And this list is not complete. I know it's not complete. I'm sure I missed your project, and I apologize. But I'm just highlighting examples of projects. So as part of my program, NITARP, which I'll talk about a little bit later in this talk and later today, I've got a web page that has a very, very long list of programs that get real data into the hands of teachers and students. So if I am missing your project in this talk, check this website and make sure I'm not missing your project there, okay? So this master list of programs is something I go to all the time. So at the very least, I would love it if we could help each other advertise, because I am recruiting right now teachers for my 2018 class, and I have about 100 teacher alumni who would love to help you figure out how to debug your program. So at least, let's help each other advertise, and at best, let's try to integrate some of these resources. So, citizen science, like I said, at its plainest, it doesn't require lots and lots of programming and astrophysics, and everyone can participate, even young children. And it is real science because it's generating journal articles. But it is definitely removed from the scientific process, which is way messier than you can convey in a simple interface. But the best kind of citizen science gives hooks for people to go deeper if they want. So you probably are familiar with Zooniverse. Zooniverse has many, many, many different astronomy projects to choose from. But one of the things I really like about Zooniverse is that it gives you hidden hooks with ways to go further. So again, following the philosophy of reaching as many people as possible, you might not know, because I only relatively learned, that Zooniverse has an enormous quantity of already developed lesson plans that fit into their program. And so again, that's supporting educators who are just getting started with using astronomy and data. I am peripherally involved with this Zooniverse project called Disk Detective. And this is one of the pages from the Disk Detective project. And so I didn't sign in for this, but you can sign in, and there's the thing you're supposed to be looking at. But look, this down here, hidden in the corner, which I'm sure you can't read in the back, is the IAU compliant coordinate-based name. So if you're looking for it, you can go deeper. You can go find more information about this object beyond just the picture it gives you on the web page. And there's a link to learn more about the object in Simbad. And this chat field allows you to talk with some of the experts who are working on this project. So it gives you hooks to go deeper if you want. And what's really interesting to me about the Disk Detective project is basically they used Zooniverse to find the most capable amateurs they possibly could worldwide. And those highly capable people, the ones who are most dedicated to Disk Detective, are now heavily involved in the weekly science meetings. They have weekly Google Hangouts involving amateurs from all over the world. And so those amateurs are getting exposure to the real science process, and they're already, therefore, working down the funnel. So for each one of the projects I'm going to highlight, I'm going to tell you what kind of data they're using, what kind of software they're using. This group, this Disk Detective group, is largely using mostly IR data, but it's all professional data that they're using. And they're using the Zooniverse interface, but that inner circle of people, those most capable volunteers, are heavily involved in getting new data. Some of them have gone on observing runs with the professional astronomers. So another project is the SDSS Voyages. Is Kate Meredith here? She was here yesterday. I'm sure she'll be here. She works with the Sloan Voyages program and the slightly older Sky Server projects. I love these projects. So this is the Sloan data, these Sloan activities. They're all working with the professional data from Sloan using that interface from Sloan. And all of the materials that they have, basically they're taking you from the very beginning through the more advanced materials. And so the thing that I really like about this project is that they are heavily trying to help you build skills and scaffolding so that you can go farther if you want. The basic idea, the model they have is do their example, but then you can use those same skills to do other projects within the Sloan universe. And the software they're using, they're working directly with the databases, the professional interface, and you have to develop some data management skills in order to do this. So there's projects that use, colors and color magnitude diagrams, spectroscopy, and galaxy morphology, lots and lots of good stuff. So the RBSEU, so research-based science education is RBSE, and this RBSEU is specifically for undergraduates. It's with Travis Rector at the University of Alaska at Anchorage, and also Indiana University. This is a descendant of the RBSE and TL-RBSE projects, which were aimed at educators and run out of NOAO. The goal of this particular project is specifically to test the effectiveness of doing research in undergraduate courses. Spoiler alert, it does make a difference. They have many different really solid exercises using real data, professional data from several different telescopes. Some of these labs are very easily extended to use new data that the students acquire. The software they're using is ImageJ and graphical analysis primarily. The PULSAR Search Collaboratory, we heard about this from Dr. Bloomer yesterday. It's run out of West Virginia University and NRAO. Basically, the idea here is the Green Bay telescope was down for repairs. It couldn't move. It could only stare at the same chunk of sky, or stare at the sky while the sky moved past, and they collected data while they were doing that. And so they looked for new pulsars in that data. So since that original infusion of data, they've gotten more data. They're, of course, using professional data. Sometimes the teams get additional follow-up data if they find a pulsar. This project, too, is generating research journal articles, referee journal articles. They don't have any generally available lessons or materials. You have to register with them. You have to do the training in order to get data access. And they provide training for teachers and students. And is Dr. Bloomer here? Yeah, do you still use Presto, or is there something else that you're using? Use Presto, okay. So the project you're going to hear about later this morning is ISAC, which is the International Astronomical Search Collaboration. It's run out of Hardin-Simmons University and many different collaborator institutions. Their goal is to work with asteroids, near-Earth objects, and comets. They have optical data from many, many, many different professional telescopes. They have online training for teachers and students, and it is an international project. They have people all over the world. And their work is organized around months of campaigns, either 1 or 2 months of intensive data acquisition. And the software they use is Astrometrica. Now working even further down the funnel, this one is working with but also contributing real data. This is MICROOBSERVATORY. I have to confess that I didn't know until yesterday's talk that they've been going for 20 years. I did not know that. I had known about them specifically in the context of the Laboratory for Study of Exoplanets. And this is wonderful. It's a wonderful, wonderful project where they're using data from their archives or data that you obtain via their robotic telescopes. They have really well thought out lessons to scaffold the users through the project. You can, using their telescopes, target any of a set of known exoplanet host stars that are bright enough to do with this. And they even have a transit calendar. So barring weather, you're guaranteed to see a transit. You have to use their web-based software to do that. Then working further down the funnel, there's a program called GEONS, the Geomagnetic Event Observation Network by students. This is part of the education and public outreach that goes with a satellite called THEMIS. And this is run out of Berkeley. It's studying, the THEMIS satellite is studying the interaction between the solar wind and Earth. So what the GEONS project does is if you are at a sufficiently rural school, they will ship you the hardware and let you help them take data on the Earth's magnetic field. But you have to be sufficiently rural that you're going to get real data. So they are specifically targeting very, very rural schools. This project primarily works with teachers, and through them, their students. They have lots of curriculum on their site covering the real basics through actually working with the data. They don't have any special software that you need to do it. I think I'm preaching to the choir when I talk about AAVSO, because we've talked about it several times already, and there'll be more talks later today. Basically, I want to emphasize in this context that you're using your own telescope or from their quote-unquote amateur telescope networks. They have lots and lots of activities, lots of ways to learn, lots of ways to figure out how to do it so that anyone can contribute to understanding. So they have networks of mentors, they have lots and lots of online training. It's really, really nice. And you don't need any particularly special software, but in order to do this, you have to know what you're doing. You have to be able to take high quality data and do your own photometry to that level in order to contribute. Further down the funnel is my project called NITARP. NITARP is the NASA IPAC Teacher Archive Research Project, or program rather. I'm at Caltech at IPAC. This program partners small groups of educators with a research astronomer for a year-long research project. And there are 2 educator alumni from NITARP here. You want to raise your hands? There's one, there's another. So if you want to talk to them about the participant perspective, they're the people to talk to. The unifying theme here is IPAC. So you have to use data housed at IPAC. Fortunately, that's really easy. because 10% of all referee journal articles worldwide use data that's housed just at IRSA, which is just a piece of IPAC. So there's so much data, it's easy to find projects that use data at IPAC. This project is specifically aimed at teachers, and we reach the students through the teachers. This project culminates in going to the American Astronomical Society meeting in January with science posters that are presented in the science sessions. They're not under a sign that says, please be nice to these people, they're teachers. They are in the same session as all the other science that matches what they're doing. In other words, if they're doing AGN, they're in the AGN sessions. Each project does something totally different, so I can't tell you reliably which software packages are used, but most of the teams use Excel because it's commonly available, and we use professional astronomy tools as we need them. Okay, then you may have heard of research experiences for undergrads, or REUs. It turns out there's also something called RETs, research experiences for teachers. This is run by the NSF, and I can't find them broadly available in astronomy. They are flourishing in other fields. If you want an educator who does biology or chemistry, there's lots of RET options, but I can't find them broadly available in astronomy anymore, except that I keep hearing that NRAO is offering them. So I don't know exactly how NRAO is doing this. But the idea here is that the RET is just like an REU. It's a summer experience, it's paid. You are at a site with lots of other teachers who are doing this project. And so there's organized events during the summer to unify this cohort of educators. And the RETs are focused just on teachers. There's no students involved per se, but the students feel the influence subsequent to the teacher's involvement in the program. And then we heard yesterday about at least one of these high school student summer programs, the summer science program. This specifically is a residential program that's been operating for more than 50 years for high school students doing asteroid work. There's also programs like Duke TIP and MIT and Caltech have similar programs. They're not necessarily just astronomy, and they're not residential, but they do try to find the best high school students they can to do real research in the summer. So I've noticed some recurring themes. I forgot to hit my timer. How much time do I have left? Okay, so there is definitely some recurring themes that I've noticed here. Everyone's goals are pretty similar in these projects. They're trying to give people a better sense of how science works, let them peek behind the curtain, give them better critical thinking skills, sometimes better computer skills or engineering skills. Many of these projects provide linkages to standards like the NGSS, but most of these projects are not strictly constrained by the standards. The teams that are developing these projects, the best ones really do involve both students and, well, both scientists and educators. And they don't assume that they can just fill in the gaps, that they don't assume what those constituencies need or want or can contribute to the project. Money, everyone's got trouble finding it. Evaluation, yes, everyone needs to do a better job. They need to find money, they need to find people and time to do it right. But as, you know, at least the best ones are learning from their participants and refining their project in response to what the participants are telling them. So you need to listen to the participants saying what they need or what they want, or after they go through the program, what they appreciated from the program. And there's a Buxner poster upstairs that it talks about some of these evaluation issues as well. Also, just in terms of sharing lessons learned, which would be relatively simple, or the more sophisticated education research, yeah, everyone has trouble finding money and people and time to do it right. The audiences, some of the projects are aimed specifically at teachers, some of them are teachers and students, some of them are aimed just at students, but what's really nice is that many can be used. There's enough resources online that the students can do it on their own. Now, when I think back to what I wanted to do when I was in high school, oh my gosh, so jealous of the high schoolers now. They have so many choices, so many ways to get hands on real astronomy data. Another theme that I've noticed is the idea of confidence building, giving teachers the confidence to do this. Because if you think about it, the teachers are used to being literally the smartest person in the room. They're used to having the control of understanding the material thoroughly. And so a lot of these projects have had to really specifically work on giving teachers confidence to not know all the answers before they start. And also, after they go through some of these projects, then they know how to take on these difficult projects. And I suspect that's probably also an issue for any adult learner, is giving them the confidence to deal with the data. I think in the future, we're going to need to think hard about how to make sure that the audience includes underrepresented minorities and differently abled audiences. Lots of these programs have lots of online resources and materials. They are varying degrees of depth and completeness, varying degrees of testing and robustness, but it would be nice to share that information. And there are central repositories like ASTRO-EDU and NASA Wavelength, but there are some barriers to doing that. For example, NASA Wavelength, if you have, say, like astronomy picture of the day, that can't go into NASA Wavelength because it changes all the time. Once you get your materials into NASA Wavelength, if you do so much as fix a typo, you have to go through the review process again. So that's a problem. Scalability, the more interaction with your participants that a project needs, the more difficult it's going to be to scale up. And the only ways that I can think of to solve that is a train-the-trainer model, like AAVSO has the networks of mentors, or specifically having lots and lots of online materials that are very robust. Few projects, justifiably, are for the true novice. Really, the participants have to be actively learning to get up to speed in order to participate in these projects. It'd be nice to be able to integrate these projects so that we can refer people to other projects up and down the funnel. Most of these projects are very structured. The participants are not just given keys to a telescope and left to wander. So that means, in more formal language, it's not really open inquiry, but guided inquiry. So you're working within the project's framework. But in contrast, you may have resources to go further, but in those cases, the participants have to have the confidence to be willing to work outside this program structure. There's also the issue of follow-on work. What should you do to keep the participants engaged after they go through the program? And especially when you have limited resources, what fraction of those resources should go to repeat customers, people who've been through the program? You want to support their interests, but then if you're spending time with people you've already worked with, what does it mean for new people? Software, as I'm sure we're going to be talking about later today, is a huge barrier because schools have difficulty installing software often. The online collaboration tools have gotten better and better, and I'm sure they will continue to improve. I don't have any really good solution to the issue of software. Web-based tools are probably the answer. I still don't know of any web-based tools that do research-grade photometry. That's one of the big holes. I know there are several different efforts right now. I'm a co-I on at least 2 that are trying to do research quality photometry on web-based tools. And there's also web-based tools that lower the barriers for, say, visually impaired students. The iData program working with Skynet is working on that. And one of the things we talked about yesterday briefly at the end of the day is archives. And I wanted to highlight some of that because the archives are getting better all the time. And many of these projects have the teachers and students accessing the professional databases with the same tools that professionals use. And the science archives are working towards more and better tools, integration of archives worldwide, and specifically workspaces at the site of the archive. So you may think of archives as just being a collection of unreduced images, but that's not the case. Archives have fully reduced data, including photometry, spectroscopy, already reduced, ready to go. And the barrier then to use by professionals or educators or the public is much reduced if you already have the photometry done. But you have to have research-grade photometry. You can't just dump anything in the archive. So just to highlight, because I've had several conversations where people didn't know this, the existing astronomy archives include literature archives spanning the 1800s through this morning, all wavelengths, radio to gamma rays, all objects, Van Allen belts, through the cosmic microwave background. The astronomy community, as I mentioned yesterday in the discussion, is moving towards big data. So the data are too big for me to take home. For years, it has been, give me the data, let me take it home, and I'll write the program here and work with it. But that is not the future. The future is, give me tools to do the analysis next to the data, and then we take home just a piece, okay? So this is an enormous advantage for educators and students as well, because you don't have to write your own code then. You can use the tools in the archive. And I think Python and Jupyter notebooks are going to change the degree of programming that educators and students can do. So if you are in a project that's taking you data and you are getting it into the archive system, then other people will use it too. I wanted to highlight, just because I work for IRSA, the Infrared Science Archive, this is, we have a similar interface to many different data sets. So this specific tool is called Finder Chart, and you put in a target and it gives you the same chunk of sky from several different surveys. You can get a color image, you can overlay catalogs from the surveys. So here I've got a plot, so there, the yellow symbols there are the objects in the WISE catalog, and down here I've made a plot from the WISE catalog. And what makes this really powerful is if I click a point in this plot, it's highlighted on the image. If I click a point in the image, it's highlighted in the plot and the catalog. So it's all interlinked and very, very powerful. You can also pull catalogs from other sources and overlay them. You can also dig up all the literature on this source, which is M101. You can find other measurements of M101. Assuming I have a viable network connection, I'm happy to give you an on-demand tutorial anytime later today or tomorrow morning. I have to go to a conference at the other end of California and give a science talk on something totally different than this on Thursday morning. So I have to leave here Wednesday at lunch. So catch me before then, or you can look for the IRSA YouTube feed. The bonus of that is that you can slow me down and you can turn on closed captioning, and you can rewind me, and you can listen as often as you want. If you don't get a chance to catch me, you can either send me email or see the IRSA YouTube feed. And just again, because it came up several times yesterday in conversation, this is one of IRSA's newest tools working with time series. This is specifically WISE data. This particular one is an RR Lyra with a period of about 0.7 days. There's the data tables in there, and those are the individual data frames that went into that. You probably can't see it, but there's little error bars on that plot as well. So specifically in the context of yesterday's panel discussion on pipelines, several of you were saying, oh, we should use ZTF's pipeline. Where does ZTF's archive live? IPAC, specifically IRSA. You were saying, oh, let's use LSST's pipeline too. Guess who's developing the LSST user tools? IPAC. And they're working closely with IRSA. So there is a theme, okay? So you can't, when you're thinking about taking advantage of programs like LSST and ZTF, don't just think about the pipelines. Think about what you're gonna do after it goes through the pipeline. Take advantage of the archives and the user tools that go with them. So both LSST and ZTF are gonna be integrated into that archive ecosystem. So my question to you guys running programs, do you have an archive? Is it part of the archive ecosystem? Will astronomers find it accidentally, or do they have to specifically know your project's name before they find your archive? So just some closing thoughts. The ecosystem of programs that get real data into the hands of students is vast, and it's important all levels of it. I can think of it as in terms of a funnel where you're pulling off the most interested people at each level of the funnel until you get to the bottom, but all of it is important. And I find them that fall into 4 categories: the citizen science, using real data, contributing real data, or original research. The programs that require more out of their participants tend to reach fewer people, and the programs that tend to reach fewer people tend to also require more out of their participants. But I suspect that these programs that don't reach many people but do require a lot out of their participants have a bigger impact on their lives. One of our teachers told us at one point, I lay awake at night thinking about data, okay? All these projects are trying to help the wider world understand how science works, how to think critically, because Lord knows we need it. Also, everyone needs money. Everyone needs better evaluation. There's lots and lots of shared resources out there. Go find them. Go to the website I put at the beginning. Go find them and share them with your teams. Most of these projects are structured, but the best give you trails of breadcrumbs to follow to go deeper if you want. And don't forget that the professional astronomy archives are moving towards features that are going to benefit you, because there's tools and interfaces, because the professional astronomy archives have to make archives that work for the professional astronomy community, which means everyone from a summer student just getting started on her first research project to an emeritus professor who can barely read his email, and everybody in between and educators and students fall on that spectrum as well. So thank you.
So we have some time for questions. That was a lot of stuff. I'm sure there's going to be questions, if not now, throughout the day. But are there questions?
Or should I just shout? Okay, I'll just shout. Thank you very much. That was a fantastic talk. One thing that I've struggled with a lot is how you maintain participation in your program, and whether you should reevaluate the goals of your program so you appeal to an audience that's further up the funnel rather than, you know, maintaining something which is maybe a little bit further down, because your audience, if it's teachers, they're time poor, so it might not be, they might be very keen on your program, but they don't have time to write the ancillary materials to fit it into their school's quite tight curriculum.
Yeah, that is a difficulty, yes. Trying to maintain interest, that's part of why I want to make sure that we all help each other, right? Help each other find more interested people, right? But you're right, I would love to have enough money to run a more formal institute, right? Where I can take teachers who are not yet ready to do research and get them trained so they are ready. But I don't have that kind of money. But between all of us, we kind of do, right? So if we can do a better job of integrating these projects, then I can, you know, with something like NITARP, where I'm working fairly low down the funnel, right, I can depend on you guys and some of these other projects to train the people that aren't yet ready to do research. But you're right, that is a really, really tough question. Yeah?
You mentioned evaluation. I wonder if you could comment on research.
Yes.
The educational research side of the projects.
Yes, we need to do a better job of doing the educational research. There's just not enough money or time. Perhaps incorrectly, I think of evaluation and education research as being closer to each other than either is to astronomy per se. But yeah, we need to do a better job. And I personally am trying to get there. I just submitted my first education research paper a month ago. So I'm trying to get there.
Just kind of following up to that, what kind of research, educational research methods do you think of projects need? Because there's a lot of, there's surveys, there's interviews, there's focus groups. Did you find in your do you see in your review any sort of themes or recommendations, best practices that you recommend?
I think there's not enough information to get best practices yet because so few people are doing it, right? For most, at least for my project, we don't have the resources to do interviews, so we are stuck just using surveys and self-reporting evaluations, which is less than ideal, but it's what I have resources to do, right? Is there another question? Yeah.
I'm not sure if this is relevant in the US or not, but I'm wondering if you've got any comments on the penetration of these activities in government schools versus private schools yet.
That is a good question. I don't have the information for any projects other than mine. Mine is 60% public schools, 40% private schools. So it is also perhaps surprisingly state dependent. Here in the US, schools have lots and lots of local controls. So every state would be different, and even every school system within the state would be different. Like the test that my son takes in the Glendale Unified School District in around LA is different than what his colleagues at Pasadena USD might take. So, and different states have different restrictions on their teachers. For example, that southeastern belt of South Carolina through Louisiana, right? I mean, they have lots of restrictions on their teachers. Some teachers are literally given scripts, like on Tuesday the 20th, you shall cover, right? And so teachers like that don't have enough flexibility to incorporate even the citizen science aspects because they just don't have that flexibility. So, run for office, yes? Yeah.
For some of those citizen science projects that are absolutely amazing because they pretty much immerse people inside, we don't have any statistics on demographics. But as you pointed out, we really need to open these fields to diversity. Any ideas, any thoughts on how this can happen?
We need to involve people from those communities on our teams. If you want to specifically involve visually impaired students, then get some visually impaired teachers or people that work with visually impaired students on your team to tell you what you need to do. But yeah, I mean, look around, right? We have to have more diversity involved.
So a couple of these questions are sort of skirting around this issue, but I think miss a central part of it. A lot of our programs seem to work really well with teachers who are already great teachers and really interested in science. And when you go to look at the impact, you have to question whether the program is actually having a big impact or not, because it's quite possible that those teachers would already be having a great impact,
Yep.
not with your program, than with some other program.
Yep, so the best evidence I have, and so there's a really nice paper that appeared in Science a couple years ago, and it was a very carefully controlled chemistry teacher experiment where they took teachers of comparable enthusiasm and skills and depth, and they put half of them into a project that let them do research in the summer. And then in New York State, they have something called the Regents exams that the students have to take. And they looked at the scores of the students, the teachers who didn't do the research, and scores from the students, of the teachers who did do research. Now mind you, the students aren't involved in the research. They just are being taught by teachers who have done the research. And the kids passed, the kids who were with the teachers who had done real science, passed the Regents state science exam at higher rates with higher scores, just by being taught by someone who has a better understanding of science. So that's the most controlled experiment that I know of. But yeah, I think your question is valid. Who are we reaching? And can we improve that reach? I think that's a very valid point.
All right, well, let's give her another